Page 3 of discrete random variables. I put the first two problems on this extra sheet because I'm going to draw some diagrams which you may or may not need to reason through these problems. A bag contains 5 blue and 3 green tickets, and a number of tickets are randomly selected without replacement. We let random variable x denote the number of blue tickets selected. Find the probability distribution of x if 2 tickets are randomly selected. Remember when we used to do probability problems with probability tree? We're going to do probability tree to show how you should reason through this problem. So on the first draw, you should be choosing between blue and green tickets, and the second draw, you are also choosing between blue and green tickets. So you have 2 draws, so you have 2 branches. You write the probabilities on each branch. So the first draw, when you're choosing blue, you have a 5 out of 8 chance of getting blue. You have a 3 out of 8 chance of getting green. On the second draw, since it is without replacement, you're going to have 4 blues remaining instead of 5. So it would be 4 out of 7 tickets remaining instead of 8. And so green would be the complement of that. It would be 3 out of 7. You still have 3 greens remaining because you haven't drawn any greens out. The next one, it is the opposite. The probability of getting a blue on the second one, you still have 5 blues remaining, so it would be 5 out of 7, and then, of course, 2 out of 7 green. In order to get the probability of each one of these paths happening, remember you just multiply the 2 fractions together. An interesting thing happens when we do this, which is going to help us on the next one. This top one is 4 times 5 on top, 7 times 8 on the bottom. The bottom one is 2 times 3 on top and 7 times 8 on the bottom. But look at the 2 middle ones. 3 times 5 on top and 7 times 8 on the bottom. Both the middle ones have the same result, even though they're done in different orders. So blue-green and green-blue, even though they happen in different orders, have the same probability of happening. So that's going to be useful later. Okay, so let's make our probability distribution table. In our probability distribution table, we have the little x variable, which is going to represent getting 2 blues, or 0 blues, or 1 blue. And then we have the probability that random variable x is equal to 0, 1, or 2. And so the probability of getting 0 blues is going to be 2 times 3 on top and 7 times 8 on the bottom, right? The probability of getting 2 blues is going to be 4 times 5 on top and 7 times 8 on the bottom. And the probability of getting 1 blue is these 2 probabilities added together. So it would be 2 times 3 times 5 over 7 times 8. So that would be 3 times 5 is 15, times 2 is 30 on top, and 7 times 8 on the bottom. You can kind of check to make sure everything's okay by adding up all the numerators. 20 plus 30 plus 6 gives you 56. So the probability of any one of these things happening is 56 over 56, 1. Perfect. Okay, let's try to do the second one without drawing the probability tree. Just by listing some of the possibilities. So if you have 3 tickets randomly selected, the first, the easiest option is blue, blue, blue. To draw blue, 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 we're just going to use reasoning here. So in the first blue, the probability of drawing the first blue is 5 out of 8. The second blue would be 4 out of 7 because we have 4 blues remaining out of 7 tickets remaining, and the last blue would be 3 out of 7, right? So that would be 3 times 4 times 5 divided by, it would be 6 here. 6 times 7 times 8. So that would be the probability of 3 blues. What about the probability of 3 greens, which is also pretty easy, or 0 blues? It would be, there's 3 greens to start out with, then there's 2 greens after we draw out the first green, and then there's only 1 green remaining. So that would be 3 times 2 divided by, this would be 6. 6 times 7 times 8. What about 1 blue? 1 blue could be drawn blue, green, green, blue, green, 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 blue, green, or green, green, blue. And remember, from what we saw here, any one of these three, even though they're three different orders, is going to have the same probability. So we just need to find one of these and then multiply it times 3. So the probability of getting blue, green, green would be 5/8 to draw the first blue. Then it would be 3/7 to draw the first green, the second ticket. And then it would be 2/7 to draw the other, oh no, it would be 2/6. I always make that mistake there, don't I? So that would be 6 times 7 times 8 on the bottom, and then it would be 2 times 3 times 5 times 2 on the top. What about 2 blues? So that would be blue, blue, green, blue, green, blue, or green, blue, blue. So all we need to do, since there's 3 possibilities, is to figure out the probability for one of these and multiply it times 3. So to get blue, blue, green, it would be 5/8 times 4/7 times 3/6. So it would be 3 times 4 times 5 times 3 divided by 6 times 7 times 8, right? And then last of all, oh, we already did them all. So those are all the possibilities. 3 blues, 2 blues, 1 blue, or 0 blues. Now we can fill in the table. Probability that, what is it? Oh, X. Probability that random variable X is little x, 0, 1, 2, 3. So the probability of getting 0 blues is this. So it would be 6 over 6 times 7 times 8. 6 times 7 times 8 is 336, so it would be 6 over 336. Probability of getting 1 blue is this. So the bottom is 336. The top would be 2 times 3 times 5 would be 30, times 2 is 60. Probability of getting 2 blues is this. So the bottom is 336. The top would be 3 times 4 times 5, which is 60, times 3, which is 180. So it would be 180 divided by 336. And the probability of getting 3 blues is 3 times 4 times 5 on top, 6 times 7 times 8 on the bottom. 3 times 4 times 5 is 60. Is that right? 60? 3 times 4 times 5? Yeah, 60. And the bottom is 336. I think one of these is wrong. What about this one? 2 times 3, 6. 6 times 5, 30, times 2, 6. Oh, it should be times 3. This is 3. So that would be 90. 1 blue would be 90. Okay. If I added up 6 plus 90 plus 180 plus 60, I would see that I would get 336. So that's a good check. All right. So that's it for problem 9. But if you feel better, always do the probability tree. On the exam, they're probably not going to give you a problem that has 3 draws, so time is really not a problem. When a pair of dice is rolled, capital N, random variable N, denotes the difference between the numbers on the top faces. Display the possible results in a table. Okay, so, to figure out these probabilities, you might draw a list of all the ways it can happen. Remember that one of the ways that's kind of good to draw 2 dice rolls happening is a table that may look kind of like this. And since we're talking about differences between dice, it might be useful, instead of making a grid, to make a table with open cells. And then in the cells, we can write down the differences. So 1 minus 1 is 0, 2 minus 1 is 1, 3 minus 1 is 2, and so on. 2 minus 1 is 1, 2 minus 2 is 0, 3 minus 2 is 1, and so on. So that we're going to start creating a pattern here zeros are going to go down the diagonal, ones are going to be next to the zeros, and then so on. So you can see how it's pretty easy to fill this table in. So that was our table. Oh, the possible results. So the possible results are 0, 1, 2, 3, 4, 5, right? 0, 1, 2, 3, 4, 5. Probability distribution table. So in the probability distribution table, we're going to have 0, 1, 2, 3, 4, 5 as our possible differences. And then the n, the random variable n, is going to be equal to these little x's. And we'll put a probability of that happening. So what's the probability of getting 0? It would be 1, 2, 3, 4, 5, 6 ways of that happening out of total of 6 times 6, because there's 6 times 6 cells. Probability of getting 1. So there's 1, 2, 3, 4, 5 times 2, 10 ones. Divide that by 36, 2. How many 2's are there? 1, 2, 3, 4 times 2, 8 divided by 36. 3 is 6 divided by 36. 4's there's 4 out of 36, and 5's there's 2 out of 36. And if we add up 6 times 10, 6 plus 10 plus 8 plus 6 plus 4 plus 2, we should get 36. Yes, we do. Okay, so that was a good check. So that was the probability distribution table. Find the probability that n equals 3. Oh, that's easy. 36, or 6 out of 36. Remember from the probability chapter, it's better not to reduce the fraction. Find the probability that n is greater than or equal to 3, given that n is greater than or equal to 1. So remember, conditional probability. Look on your formula booklet. On your formula booklet, it says that the probability of n is greater than or equal to 3, given that n is greater than or equal to 1, is the probability that both are true and divided by the probability that this one is true. What's the probability that n is greater than or equal to 1? Everything added together. So basically it's everything except for 6 out of 36. So wouldn't that be 30 out of 36? What is the probability that n is greater than or equal to 3 and n is greater than or equal to 1? Well, for both to be true, you can only have n is greater than or equal to 3. So this is actually irrelevant in this case. If you're greater than or equal to 3, you're also greater than or equal to 1. So what is the probability that you're greater than or equal to 3? 6 plus 4 plus 2, 12 out of 36. 12 divided by 36 divided by 30 divided by 36. I know this is like the hardest part of the problem. Dividing by a fraction is the same as multiplying by its reciprocal. Canceled. 12 over 30 is the answer. Okay, that was the first two problems. 23C, expectations. Okay, if you roll a dice 120 times, how many times do you expect to roll a 6? What you do is you take the 120 times you are doing the experiment, and then you would multiply times 1/6, which is the probability that you would get a 6. So you would expect to get 26s when you roll it 120 times. How did you calculate that? I took the number of times I rolled it, and I multiplied it times the probability. How do you calculate the expected value of x from the outcomes x and the corresponding probabilities p? So that would be like expected value is basically the same as like the average of the results. So like let's say that you roll a 6-sided dice. What do you expect the average value shown to be? So in that case, what you do is you'd say, okay, I'm going to take the probability, I'm going to take the outcome 1, and then I'm going to multiply it times the probability I get a 1, and then I'm going to add that to the outcome 2, multiply it times the probability I would get a 2, and do the same thing with each outcome and multiply it times the probability for that outcome to happen. Oops, plus. Okay, so that's how I would find the average result if I rolled a dice a bunch of times. It makes sense, right, that it would be like 3.5, because like if you would take all the numbers from 1 through 6 and you add them all together and you average them, you would get 3.5. If I was to write that in math, I would say something like, I'm going to take the first outcome, multiply it times the probability of that outcome happening. I'm going to add that to the second outcome and the probability of that outcome happening, and so on, all the way to the last outcome. I don't think that really helps you, right? Okay. If the game is fair, what is the expected gain? So think about in gambling. If you have a fair game, sometimes you win, sometimes you lose, but on average you break even. So the expected value of a fair game is 0, the expected result of a fair game, okay? Sometimes you win, sometimes you lose. You should win and lose the same number of times. In a particular region, in a fair game, in a particular region, the probability that will rain on any one day is 0.28. On how many days of the year would you expect it to rain? Okay, there's 365 days in a year. I would expect it to rain 0.28 of the 365 days, right? 0.28. 102.2 days. Okay. Sometimes on the IB exam, if it's like 102.2 people, they would expect you to not put 0.2 people because they don't want you to cut people in half or whatever. I don't know if what's wrong with saying 102.2 people. I mean, you're not really going to cut them in half. You're just saying that it's between 102 and 103 people. If 2 dice are rolled simultaneously 180 times, on how many occasions would you expect to get a double? Oh, okay. So getting a double would be getting like a 1-1, a 2-2, a 3-3, a 4-4, etc., all the way up to 6-6, right? What is the probability of getting a double just rolling one time? Well, the best way to figure it out is to draw a list or a diagram. Remember, if you have a diagram that like we did before, we had this diagram, right? In how many of these 36 cases do we get a double roll? It would be basically all these ones going down the diagonal, right? So there's 6 ways of getting a double out of 36 rolls. So one time it would be 6 out of 36 or 1/6, right? If we roll the dice 180 times, basically we're saying 180 times, 1/6 of the time we're going to get a double. So that would be 180 divided by 6, which is 30. During the snow season, remember this is NP. We just used NP here. During the snow season, there is a 3/7 probability of snow falling on any particular day. If Udo skis for 5 weeks, on how many days could he expect to see snow falling? 5 weeks, and this is given in days. So I think we should convert one of these. Let's convert 5 weeks into days. That would be 5 times 7, which is 35 days, right? 35 days, there's a 3/7 probability on any day of snow falling. So that would be 35. 3/7 of the 35 days we should expect to see snow. So 35 divided by 7 is 5, so 15. You could do that in the calculator. So on 15 days, we would expect to see snow out of 35 days. 7. In a random survey of her electorate, politician A discovered the residents' voting intentions in relation to herself and her 2 opponents, B and C. The results are indicated alongside in this nice table. Estimate the probability that the randomly chosen voter in the electorate will vote for A. So first of all, I'd like to know what the total is so that I know what the denominator is. So 165 plus 87 plus 48. So, the total is a nice round number, 300. Estimate the probability the randomly chosen voter will vote for A. So it would be 165 divided by 300. What about for B? 87 out of 300. What about for C? 48 out of 300. Okay. If there are 7,500 people in the electorate, how many of these would you expect to vote for A? Okay, so this would be 165 over 300. This is like the kind of thing SAT likes to ask, right? So you don't really need a unit in this to reason through this, which is why, SAT likes it. 4125. 87 times 75, I'm doing B now, divided by 300. 2175. And last of all, 7,500 divided by 300. This is going to come out to be a nice number. 25. So 25 times 48. 1,200.